Today, we're going to step into the lab to solve a really neat chemical puzzle. We're looking at something called bromatometry, which is a super clever technique that uses a simple, dramatic color change to measure something that's, well, completely invisible.
So, let's start with this question. How do you do it? Imagine you're a chemist. You've got a beaker full of liquid, and you know there's something specific dissolved in there. But you can't see it, you can't weigh it, so how do you find out exactly how much of it you have? Well, the answer involves a pretty cool chemical trick and a very clear visual clue.
Now, to get how this trick works, we first need to talk about the fundamental process that makes it all possible, the redox reaction. Honestly, the best way to think about it is like a carefully choreographed dance where electrons are constantly moving from one partner to another.
You see, a redox reaction always has two parts happening at the exact same time. First, you have oxidation. That's when a substance loses electrons, which makes its charge more positive. And then you have reduction, where another substance gains those very same electrons, becoming more negative. It's a perfect little partnership. One gives, the other takes.
And here is the absolute most important part. These two things are totally inseparable. You cannot have oxidation without reduction, and you cannot have reduction without oxidation. They are two sides of the exact same chemical coin. Every single electron that gets lost has to be gained by something else, period.
Okay, so with that electron dance fresh in our minds, let's meet this star of our show, this clever redox technique called Bromatometry. This is how we put that whole principle to work to solve our invisible substance puzzle.
So what is it exactly? Well, bromatometry is a type of titration. And all titration means is that we're carefully adding one solution to another to make a reaction happen. In this case, we use a chemical called potassium bromate. This stuff is a really powerful oxidizing agent, which just means it is fantastic at grabbing electrons from other substances. And we use that ability to precisely measure the amount of our target chemical.
Now, like any good recipe, this whole process needs a few key ingredients, and each one has a very specific job to do to lead us to that final color-changing clue. All right, let's meet the players. First up, we've got our potassium bromate. That's the stuff we're going to be adding drop by drop. The whole reaction also needs to happen in an acidic solution to even get started. Then we add some extra potassium bromide. And finally, the most important part for our big reveal, an indicator, something like methyl orange, which is what's going to give us our signal.
Okay, now this is where it gets really smart. The reaction doesn't just happen all at once. In step 1, the potassium bromate we're adding actually reacts with the potassium bromide that's already in the flask. And together they create bromine. This bromine is the real worker bee here. Then, in step 2, that brand new bromine immediately finds and reacts with our sample, oxidizing it.
So, we've set the stage, the reaction is happening, but it's all completely invisible so far. So how in the world do we know when we're done? This, right here, is where the magic happens. This is the visual aha moment we've been building up to.
Okay, just picture the scene. We start our experiment, and thanks to our methyl orange indicator and that acidic solution, the liquid in our flask is this really distinct red color. This is our starting line. Now I start adding the potassium bromate, just one drop at a time. Each drop creates a tiny bit of bromine, which is immediately, and I mean instantly, snatched up and consumed by the sample we're trying to measure. Since that bromine gets used up right away, it never gets a chance to mess with our indicator, so the solution just stays red.
We keep adding more drops, one after another. And with each one, more of our invisible sample gets used up by the bromine. That red color is holding steady, but we're getting closer and closer until, finally, we hit the critical point. The very last molecule of our sample has just reacted. It's gone.
So what happens with the very next drop we add? It creates more bromine, just like all the others, but this time, there's no sample left for it to react with. For the first time in this whole experiment, we have free, leftover bromine just floating around in the solution. And this free bromine has a brand new target, our indicator.
And there it is, bam! The free bromine instantly attacks and bleaches the methyl orange indicator. That bright red color just vanishes and the whole solution turns a pale yellow. That sudden, dramatic change is our signal. It's the end point. It tells us we've added the exact amount of titrant we needed. The puzzle is officially solved.
Okay, so this is a fantastic little technique in the lab. But what's it actually used for? Well, it turns out this super precise way of measuring things is critical in some really important real-world fields.
For instance, in the pharmaceutical industry, bromatometry is used to check the purity and exact amount of crucial drugs, like the key anti-tuberculosis medication isoniazid. And in environmental and analytical chemistry, it's used to determine the exact concentrations of elements like arsenic and antimony, which is absolutely vital for public safety and quality control.
So let's just quickly boil it all down. What are the key takeaways? First, bromatometry is a super precise measurement tool built on the fundamental principle of redox, that dance of electrons. Second, it cleverly uses a two-step reaction to create its real active ingredient, bromine. And third, the whole shebang culminates in that unmistakable color change from red to pale yellow that tells you, stop, you're done.
And that pretty much wraps it up. It's just a powerful reminder that sometimes the solution to a really complex, invisible problem is as clear and simple as a change in color. It kind of leaves you wondering, doesn't it? What other incredible, invisible chemical puzzles are being solved right now with clever visual clues just like this one?